Hello friends. Assignment of term symbols D2 ion in an octahedral environment is the subject of this present video. You must remember that in the earlier video we have talked about the splitting of d orbitals in an octahedral environment, which led to ultimately the splitting in terms of Eg and T2d set of orbitals in terms of symmetry and group theory. I'm your instructor Saurabh Muktibodh. Well, beginning, let's have some remarks on the quantum numbers for many electron systems, many electron atoms. Generally, when we talk about several electrons in a partly filled shell, we have the values of the azimuthal quantum number that is given by 0, 1, 2, 3, 4, 5, 6, and the corresponding letters are given by S, P, D, F, G, and so on. This is what we generally do as case of hydrogen atom. But when we talk about some situations where there are electronic repulsions, when there are two electrons in the same box, then the repulsions are quite likely. And for strong inter-electronic interactions, this method is just not sufficient. The behavior of real atoms often approximates closely to a limiting situation that was proposed by Russell Saunders and also known as the LS coupling scheme. This is a part of elementary quantum mechanics, as my students of quantum mechanics are familiar with. In this situation, or in the RS scheme or the LS coupling scheme, L gives the total orbital of all the electrons, and quantum number S gives the total spin of angular momentum of all the electrons that are used. For instance, if we have L is equal to 0 in terms of its capital or the uppercase, L is equal to 0, 1, 2, 3, 4, 5, 6, and so on. In earlier case, we have given the lowercase, but now we are going to depict it by the uppercase. So we have capital letters of S, P, D, F, G, and so on in the present scheme. And the term for an atom has been, put up in the form of 2s plus 1 Lj, where 2s plus 1 demonstrate the spin multiplicity, and S is the total spin, of course, and L demonstrated the total orbital angular momentum. However, here we are now coming across with a new term, that is the J term. So in general, we write a term for an atom, for an electron in an atom, by 2s plus 1 Lj. We are not actually going into details of how these have been derived, but we are just making a brief note on the entire history. There are few facts, there are few assertions, there are few properties about the angular momentum quantum numbers. And first one is, for a given value of L, the associated allowed values of ML are 2L plus 1. It means that if we have L minus 1, so on, it goes to minus L. If we have 2, then it will go to 2, 1, 0, minus 1, minus 2, and so on. For a given value of S, the associated allowed values of MS are 2s plus 1. That is, of course, define the spin multiplicity that goes from S minus 1 to minus S. For a given value of J, which depicts the total momentum, the associated values of Mj are 2J plus 1, which may have the values of J minus 1, and it goes to minus J. So these are certain facts. Continuing the same, the quantum number J has a maximum value when both L and S point in the same direction. So the net result would be obviously maximum when both points, the orbital angular momentum and spin angular moment point in the same direction. J would have the maximum value. If they are in opposite direction, it goes without saying that they would contribute least. The total allowed values of J are given by J max minus 1 up to J minimum. So if you have, say, 4, then you can have 3, 2, 1, and so on. So they are the possible values of J. In terms of L plus S, you have L plus S minus 1 up to the mod of L minus S. The situation would go like that. Atomic states arising from the same electronic configuration and having the same value of L and S are said to belong to the same term. Now, this is very important. Atomic states arising from the same electronic configuration and having the same value of L and S are said to belong to the same term. And states belonging to the different terms have different energies, since the inter-electronic repulsion is different for each atom. I am not making it very rigorous in terms of quantum mechanics, but we are now trying to use this all practice regarding the splitting of d orbital in an octahedral environment and a d2 case when there are two electrons in d orbital, this case have been the simplest case. This case would have been the type when only two electrons that make a possible space in the 5 degenerate atomic orbitals. As far as the mathematical combinations and permutations and all that are concerned, the number of ways of assigning two electrons among the 10 spin orbitals, because there are 5 orbitals, but they may have plus half spin or minus half spin, involved in d orbitals would be given by factorial g upon factorial n into factorial g minus n. So factorial g would be 10, factorial n is 2, and that's on solving gives the value of 45. And thus, there are 45 unique combinations in which ml and ms values are possibly there, and we can assign the terms for such situations. Let's try to work out. Are you ready? Yes, this is quite interesting. And let's do a few illustrations first, and then we'll quickly go through the other situations. If I talk about the first case, I would start with the first thing, that the two electrons are there in the first orbital itself, where plus 2 is there. And with this, I understand that the ml value would be equal to 4, because there are two electrons here and this is 2, this has to be 4. And because both the electrons are inverted, the spin has to be 0. They are going to cancel the spin, so this is 0. Now, what is the next possibility? Next possibility is this electron remains here. This electron remains here, and the other electron may go in the other house. And if it does so, there is a possibility that it has an inverted spin. Even then, if you talk about its ml values, then this is plus 2 and plus 1, that makes it 3. So I would write here 3. Because both the spins are still inverted, this is opposite spins still are there, it has to be a 0 value. You can see it's a 0 value. Now you can yourself judge. If you are talking about 3, the electron in is plus 2 house, still it is there, but with a parallel spin, it must be 3, and now their parallel spin is 1. We are talking about both the electrons are now here in the upward direction. Now, if you take about both the electrons in a downward direction, so if this is downward, this is downward, this still remains 3, but the negative half and the negative half would make minus of 1. In the other cases, of course, at your perusal that this electron is inverted, but this electron is not inverted, you have 3 and 0 value. So what you have been able to notice that there are 4 3s with 2 zeros and 1 and minus 1 values. This is what we have noticed. There is only 4 is 1s here, but in other situations there are 4 3s with 0, 0, plus 1 and minus 1. Well, what is the next combination? Can you suggest me? Yes, of course. Now, this electron has the same orientation here, but it is no longer going in plus 1, but it is going to 0. That is going to change its value from plus 2 to 0. That's going to be plus 2. So here you will have a plus 2 value. And if this is plus 2, both the electrons have parallel spin, this will have plus 1. In the seventh idea, you have this electron is still there in the parallel spin, but this electron goes opposite, this still remains 2, net spin is 0. For this, now there are two possibilities for 8 and 9. Both the electrons are inverted with spins parallel or anti-parallel. So that allows us to compute that is 2 minus 1 or 2 and 0. Again, we can refer that here we have 2, 2, 2, 2. There are 4 2's and 1, 0 and minus 1 and 0. So this is the way we'll be keep on keeping the electrons in different houses, and we'll be able to calculate the values of ml and ms for them separately. Let us go quickly. I'm not going to explain you. Just please watch this happening. This plus 2 minus 1. This is 1. 1. Look at this. Fine. Yes. Is it fine? You have 4 1s with 2 zeros and 2 positive and negative 1s. Now the next electron is going to change its place. So it's going to come into minus 2. That's going to change 0. So we will have 4 zeros likewise. So here 0. The next one is 0, then other one is also 0. But with the difference is that there are 2 zeros and 2 1s, that is plus 1 and minus. So this is the situation when the first electron goes to plus 2 orbital, while the rest of the possibilities are seen. Now I am just computing the next situation. Next situation is like that the electron is going into plus 1 state. If it does so, first thing is both the electrons may be there. So it's enjoying this, the spin is of course 0. But then there are 2 electrons here, and if there are 2 electrons, so 2 into 1 becomes 2, and the next spin is 0. So just watch it. It goes like this. Fine. Keep an eye. You have 2 1s now. third ones and the fourth one, and we have a combination of 1, 0, and -1. Let us change another possibility. Let it remain here, but we'll jump to -1, and in doing so we'll have an ML value of 0. Spin would be, of course, changing accordingly. So there are 4 -1s now at your parcel. The rest of the 15 possibilities are like this. Both the electrons goes to 0 state, and because 2 into 0 is 0, ML is 0 and MS is also 0. And moreover, the situations would keep on changing. We have 4 -1s, and then similarly it goes to 4 of -2, I suppose. Yes, 4 of -2 with each values of 1, 0, 0 and -1. You have 39 possibilities that you have taken into account. Go to 40 number. 40 number would take -1 into account, both the electrons. So it is -2, 0. 41 would be, now the next electron is going here, and you will have 4 possibilities for -3, right? And now we are left with only one possibility, that both electrons occupy the last house, that is at -2. So this is here, that goes to -4, spin becomes 0. So this is how we have calculated the 45 possibilities. In principle, there exist 45 combinations, and all of them have been displayed. Now what to do with this? Let's go ahead. In assigning the term symbols, what we do is we'll first find out what is the largest value of M. We have seen that ML is +4, L is equal to 4. So if L is equal to 4, then the combinations are possible as far as the quantum mechanics permitted values are from +4 to -4. There are the 9 such values. Now nextly we'll see what are the values of S. With ML equal to 4, correspondingly MS is 0, that you just go through all the options that has been displayed now. And if it is S is equal to 0, that means for all values of 4, here you have 0, this should be 0, this should be 0, this should be 0. So there are all 9 combinations are quite likely, and these combinations have been displayed by the numbers that are there. You are suggested to just pause the video and see if they are indeed there. So the value of J is equal to 4, and for L equal to 4, the term is G, and therefore I would suggest you that what to do, we have 0, 2s plus 1, that is 2 into 0 plus 1, that is so 1. And for L equal to 4, we are using the term G, and J is because it is L plus S, this will be 1G4. So this is the one corresponding term related to the D2 system. You can just examine this. This is 4 0, this is 3 0, this is 2 0, this is 1 0, this is 0 0, this is -1 and 0, this is -2 and 0, this is -3 and 0, and this is -4 and 0. So you just examine the 1, 2, 3, 4, 5, 6, 7, 8, 9 orientations have been covered. Right. Moving to the next situation, when ML equal to 3, and if ML equal to 3, the corresponding values may be +3 to -3. So +3, +2, +1, 0, -1, -2, and -3. And because you can, the highest value of ML equal to +3 is not 0, but it's +1. So if we are saying it's +1, then the MS values may orient to +1, 0, and -1. So for each value of 3, there are the values +1, 0, -1. But here also, here also, here also, here also, there are 7 possibilities, and for this every possibility you have 1, 0, and -1. That counts 7 into 3. There's 21 combinations are likely to be there, and you can yourself discover that actually there are such 21 combinations possible. And if you are saying that it's L, the term is F, and the term symbol would be equal to 3F4, right? Because spin multiplicity is a triple 8 state. There is 2s plus 1, there's 2 into 1 plus 1, that's 3F4. Just observe the conditions. We have 3 1, 3 minus 1, 3 0, then 2 1, 2 minus 1, and 2 0, then 1 0, 1 minus 1, and so on. So it will just keep on watching this entire screen. Rather, if you're interested, you can pause the video and examine the thing. And therefore, the term we propose for this is 3F4. Continuing in the same fashion, we have talked about L equal to 3. Now let's talk about the value of ML is equal to +2. So if this is +2, then L is equal to 2, and the corresponding value is 2 plus 1, 0, -1, and -2. And for each value, the maximum value of spin is 0. So it's a singlet state, and therefore there are only 5 unique combinations possible, and they have been discovered as for L equal to 2. What we propose in the term is D. So we have it's a singlet state. So 1D and the J value is 0. You can simply observe this. So 2, 0, 1, 0, 0, 0, minus 1, 0, minus 2, 0. So these are the 5 possible states. We are left with the next choice is ml equal to plus 1. If it is plus 1, then the allowed values are plus 1, 0, minus 1. But the maximum spin is 1. So then for each value of ml, there will be the 3 values. So 1, 0 and minus 1 for each value. So because there are 3 combinations here, and for each there is the 3 possibility. You have 3 to 3 is 9 such possibilities are there, and you can discover these 9 possibilities here. 1, 1, 1, 0, 1, minus 1 and so on. Just keep on watching it. If you are interested in every detail, you can pause the video at any point of time. However, we are now interested in arriving the fact that if L equal to 1, we are talking about actually a p stated, p orbital kind of thing, a triple degenerate. The multiplicity is 3 and the term is 3 phi 2. So it's that simple. It's nothing to worry about. And finally, we are left with only one thing. And that was about the 26th operation. When ml equal to 0, obviously ms is equal to 0. So when we are talking about this, the only possibility is the s orbital, which is a singlet state and has a 0 value of J. So fine guys, now we have been able to discover all the terms for a D2 electronic systems, and this is for the 26th case when we have 0 and 0. Right, so it was left only. All the situations have been now so far encountered, and therefore these are the states, or simply I can write that there are the 1D, 3F. Okay, 3 has to be there on the superscript 1D, 3P and 1S and so on. That is what we did here. All of the situations have been covered and have been discussed in the video. What does it mean is, what the states for D2 ions are, we have discovered under weak interaction for a free ion. There are possibly 3F, 1D, 3P, 1G and 1S. And as a matter of fact, actually these have been determined relative energies because they have been displayed in terms of their energies. So the relative energies are now in terms of their experimental values. Well, we will be discussing about their splitting under weak interactions and assigning the metric terms. We'll be talking this later videos, but this would be something like this. And it has to be interested to note that if this is 3, if it's triplet state, all the terms here would be triplet. If this is 1, all the terms would be singlet. If it is 3, so all the terms will be triplet. If this is 1, all singlet and all singlet. So this is how we have realized that one situation, that is the splitting of the terms in an octahedral environment, can be examined. Actually, our motto was only to assign the terms, and that we did precisely. Thanks for watching.